Recording. Okay. So that you know when I start talking. Sometimes when it's a little bit prior to class and I'm a little bit early and some of you are early and you have some questions, I usually use the chat. And then when I start the actual session, then I ask everybody if you can hear me. Okay. So let me get rid of this stupid page. My bad. Whoops. Yeah. I just send you the same content via email. Dane specifically, and everybody else, so in case you need to go back to it. Otherwise, in the future, like I was saying, either write them down or just do a screenshot with your answer filled out. So right before you submit you click the submit button, just do a screenshot of each section so that you have it on record. So that as I send the key and you look at your grade on Lolima, then you can double check. And then if I'm a mistake as I tabulate all those points, then you can tell me, yo, you know, I'm missing points here. If I give you too much points, don't say anything. Keep up. But if I didn't give you enough, then make sure you let me know. Okay, so today let's finish up 2D. Let's analyze any question you may have. Again, let's follow the exact same method as we've been doing, step by step. Then we take a quick break. Then I just want to introduce Newton, again, just the method, so you have it. So make sure you take very, very good notes. I duplicate the exact same method in C270, and I want to use C271 because that's the only one that they're going to be using for the rest of the semester. So if you feel that you're going to be seeing any directions, please make sure you take that method seriously, because if you use it, life is easy for the next class as well as this class with respect to all Newton forces. If you know what you're doing and you don't need it, feel free to ignore it, but at least you have the option. Same as kinematics. At least you have the option of using the method and to minimize the possibility of making mistakes. Again, except for the WI folks who have no choice on that matter. Okay, so questions on kinematic 2D. Is there any problem that by now you should have worked out all the problems in 2D? Is there any one that you've encountered, started, and have questions about? Or is everything okay? And can we move on to Newton? Crystal suggests problem 7, Alan problem 2 part B. Alright, could you specify which chapter? When you ask a question, let me take notes. But could you specify chapter? Vector chapter, kinematic 1D, kinematic 2D? So I have number 7, number 2 part B, and 2A. So I'm guessing 2 part A. Crystal was about kinematics 2D. Okay. What about Alan and Michael? Are you referring to kinematics 2D as well? And therefore probably the same problem? Okay. Okay. What about you, Michael? Which homework? Which chapter? Kinematic 1D or kinematic 2D or vector chapter? Which set of homework? There is a set of homework for each chapter or each topic. Alright, 2D. Okay, so we're on 2D. So let's start with the order. I'm guessing 2 might be easier than 7. So if you don't mind, Crystal, let's start with 2. Alright, thank you. And they only ask for 2A and 2D. Okay, so 2A. So we're doing the baseball player hits a ball so that it leaves the bat at a speed of 45 meters per second at 60 degrees above the horizontal. And part A is being asked, as well as part B. Please let me know, Michael and Alan, if I got the right problem. If so, let's start with part A. Wait, where's my pen? Okay. All right. Okay. The direction. Ah, okay, okay. Perfect. Excellent question. I'm guessing you're referring to the velocity. Okay, so first step, let's draw a diagram. Baseball player hits a ball, so he leaves the bat at a speed of blah, blah. So nothing is specified about Where? So we can assume it starts from the horizontal. Which this is 60. That's our V0. And remember, oh wait, no, yeah, V0 is given to us as 45 meters per second, and the angle, initial angle, is 45. So remember, when you draw a diagram, if it's a 2D, it's always going to be a parabola, never a straight line, ever, ever. So my diagram is done. The next step in the method, using the method under the test link, is to pick a coordinate system. I'm going to pick a coordinate system such that my y is positive up and my x is positive right. And I'm going to choose the origin so that it starts at initial time and initial space. Okay. So before we start answering any question, let's spend 5 minutes of using the method. Equation. So we have our usual equation right here. So make sure that if you're in a non-WI section, you memorize them, because those are the ones that you want to use. And if you're WI, you don't have to. So it's a 2D problem. Therefore, we need to break this up and look at both direction, X and Y. So this is also a free fall situation, which says that the acceleration is constant. That's first. Which also says the direction has a specific magnitude being constant, which is 9.81 meters per second squared. And third, that its direction is down. So let's look at the X direction first. Obviously, due to free fall and the fact that the acceleration is as a direction which is vertically down, and I've chosen my x-axis to be horizontal, then there is no acceleration in the x-axis. Therefore, in the x direction, equation 2, 3, and 4 lost the last term, which implies that the first and the second equation are the same. And the third and the fourth confirms that the x component of the velocity doesn't change. All right. Since we're doing a 2D motion, the x component of the velocity, as we use a vector, can be decomposed initially as v0x and v0y. Therefore, by property of a vector, v0x is nothing else but v0 cosine theta. And lastly, since I have decided to put the origin of my coordinate system at initial time and initial position, my x0 is 0. Hence, my final equation for x are x is equal to v0 cosine theta t. And just for good karma, in case we need the velocity at some other time, vx is equal to v0x, which is v0 cosine theta. This one doesn't change. Perfect. That is correct. Oh, yeah, I'm sorry. I wrote it wrong. Thank you. Thank you, Cal. So that was for the x direction. In the y direction, let's start with the initial. So again, you can use whatever order you like, based on the choice of the location of my origin, which I have located at initial time and initial space. All my initial value will be 0. Okay, I'm sorry. Let's start in order. Let's look at the y equation. Obviously, because of free fall, the acceleration is in the y direction and is constant and is equal to 9.81. Therefore, we cannot use the first equation. So we don't do 3. Similarly, since we're looking at the y component, all my x are going to become y. And here, be careful, keep your label. This is a y. Don't leave it as generic. Vy, V naught Y. Otherwise, it's very tempting to confuse it with the other V in the X direction. Okay. Now, since again we're dealing with a freefall whose property is that A is constant is equal to 9.81, we usually denote it by letter G, so we're going to change all the A with the G. And since this direction is down, and I chose to have my positive Y up, this implies that all my A will not only become G, but will pick up a negative sign. So I'm going to change all those signs. Ooh, that's a fatty one. Okay. All right, next one. Same as I did it for V naught X, due to property of vectors. My V naught Y should be expressed in terms of its component using vector analysis. So I can substitute the function of my V naught as V naught Y as V naught sine theta. And finally, since I again put the origin of my coordinate system at the initial time in initial space, all my Y naught are 0. Therefore, my final set for Y is equal to V naught sine theta t minus 1/2 gt squared. Vy is equal to V naught sine theta minus gt, and Vy squared is equal to V naught squared sine squared theta minus 2gy. Perfect. Final set of equation in both my X and my Y, which are specific to my problem. Which means that from now on, I just need to plug and pray. That easy. So, part A. Find the position and the magnitude and direction of the velocity. Okay, so for the position, after a particular time, which equation am I going to use? Let me put some numbers. 1, 2, 3, 4, 5. Which equation or equations should I use to obtain the position after a given time? Position 1 will give me the X component of the position. Is that all I need? So that's correct, I agree. Perfect. Position refers to coordinate. So what else do we need? Excellent, we need the Y, therefore we also need 3. Good. So as we need Y, we get the X, which is V naught, we plug 45, cosine of 60 times 2. Bang. And then for the Y, we just plug again, 45 sine 60 times 2 minus 9.81 divided by 2 times 2 squared. And that's in meters. Bang! Okay? Obviously, Y is positive, and X is also positive. Okay, so we're somewhere along that trajectory. Good. Is everything good so far? All right, now second part, calculate the velocity. So remember, velocity is like position. Velocity is a vector. Therefore, you need to obtain both components, X and Y. And here, to give you a hint, by actually specifying the magnitude and the direction. To remind you. So first, we need to shoot for the Vx component. Then we need to tackle the Vy. And then we can just use trig to figure out the magnitude and the direction. So, which equation are we going to use to obtain Vx and Vy, given that we're looking for those two quantities as a function of time, specifically t is equal to 2 seconds. First one, first one, what would you think the first one if we're looking for the velocity? The velocity is not showing up in the first equation, only the initial velocity. Okay, I wait. Jamie, Tyson, and Tyson suggest equation 2. Are you in agreement with them? Okay, okay. So equation 2 will give us the x component of the x. All right. And then to get the y, Cynthia suggests let's use equation 4, which involves vy and t. Excellent. So vx, whoops, vx will be equal to v naught. So equation 2 will give us 45 cosine 60 meters per second. And then vy will be obtained by equation 4, 45 sine 60 minus 9.8 times 1 times 2 meters per second. All right. For us to be able to deduce the direction carefully, we need to make sure to verify the signs. This is positive. What is the signs of Vy? Is it positive or negative? Still positive. Okay, so that means that we are before the apogee. We are on our way up. We haven't passed it. Because we know that as soon as we passed it, this better be still positive, but then Vy will become negative. So we're on the first part. Okay, good. Which means our life is easy because then our angle is in the first quadrant. So from there, we can calculate the magnitude, which is Vx squared plus Vy squared. Take the square root. That will give us the magnitude of the velocity and the direction, which we expect to be on the first quadrant because we're going to be somewhere here. This is Vx. This is Vy. Is going to be obtained by taking the arc tangent of Vy divided by Vx. Since both are positive, we can trust the calculator and we just grab whatever it gives us, which should be positive. Oh, you referring, Jamie, to Vy or theta? Oh, we just did it in our head. This is roughly 10, right? So 10 times 2 is 20, and sine 60 is 1/2. And so 45 divided by 2 is bigger than 20. Perfect. Does that answer your question, Michael? I think that was Michael who asked for 2A. All right, perfect. So now let's tackle 2D, which was Anand's. What changes in 2D? Repeat the previous question, assuming that now the ball was hit at 1 meter above the ground. So same question, except now we're going to start here. Same initial condition. (60, 45). So all we need to do is rederive the equation of motion so it's consistent with that particular change. Let's identify which equation is going to be modified due to that shift. Are my x equation going to be different? That is, as we move our initial position in the y direction by 1 meter, is that going to affect our reasoning and the functional form of our x equations? Absolutely, Cynthia and Mallory. Excellent. Since the only change is the change in the y direction, we expect the x not to change. If you're not sure, go over the same reasoning again step by step, and you're going to realize, oh, yeah, same thing. Exactly. The only difference will be in the y. So everything will be the same, except, be careful, Adrienne, it's not going to be y, but it's going to be, and I get back to you, Jamie, right after, it's going to be y naught, if we keep the coordinate system where it is. Okay, so the only change is that right here, up, and right here, up, we're going to keep our why not. And why not will be positive 1. That will be the only change in our equation. Excellent, Ariane. Okay? Does that answer your question, Alan? And then from there, you do the same exact reasoning. So it means that the only one that will differ is this little bugger. Oh, that's round-off error. That's close enough. Remember, the rule of thumb, if you're given a problem with n amount of 6 figures, keep the same amount. So in this case, everything is given to you at the maximum of 2 6 figures. So keep 3 as you do your calculation, and at the end, round it off back to 2. So in this case, well, actually, 180 would have been fine, even though that's 3 6 figures. So remember, Alan, I'm not seriously concerned about exact numbers. As you take more engineering courses, if that's the way you go, they will be, but not as physicists. We don't care. I'm more interested in the way you did it and how you manipulate the equation and how you use the method. It's rare when I take points out of one for the wrong answer, numerical answer, unless it's way off and the source is somewhere else. Okay? Same ballpark. Don't worry about it. You may have used 9.8, I may have used 9.81. Who knows? All good, all good. Perfect. Now, Amy was saying, can we be lazy and leave our coordinate system alone and solve for y is equal to -1? Yes, we could have been lazy and solve for y is equal to -1. But if we do this, then we will have to shift our coordinate system. We cannot leave it alone. That is, if we shift and choose to pick a coordinate system such that we put it here, then our equation remains the same. No change. So to me, I agree that would be the lazy way. However, as we're looking for anything, the y that you're going to measure is good, like I said, this one is going to be measured from this line, which means you have to add the additional one. So as long as you state it in words, that's perfectly fine. Does that make sense? Perfect. So usually when on test, I will always be very precise by asking you what is the position with respect to something, with respect to the edge of something or with respect to the ground, so you know with no ambiguity, you know, what's your reference frame. So if you pick a different one, then you can always adjust by adding the shifting factor. Excellent, good. Any other questions on this problem number 2? Is everything good? Yeah, number 7 is next. Okay, perfect. But you're the one asking for number 3. Should we go in order, assuming that it's order of complexity? Should we make a beer stop at 3? Okay, before we move to 7? Okay. So, number 3. Okay. So number 3, you toss a rock from your window 9 meters above the ground. Okay, so diagram first. This is the ground. This is my window. Okay, perfect, Chris. When the rock leaves your hand, it's moving at a speed of 50 meters per second, so we know V naught. And at an angle of 20 degrees below the horizontal. Therefore, theta is negative 20. If the horizontal is here, oh wait, then let me expand my 9 meters. Let's say 9 meters is all the way here. From the horizontal, so that's where you need to read the problem carefully. They're saying that we bring the rock at an angle of 20 degrees below the horizontal. Therefore, our angle is right here. That's 20 degrees. And again, this will be a parabola. Never a straight line. Okay. How far horizontally from your window will the rock hit the ground? So we're looking for the range that we mentioned last time. Okay. Okay, so we've drawn a diagram. Exactly. If, but we're not there yet. We cannot call it X yet, Kyle, because we haven't decided of a coordinate system. If I decide to put, like an idiot, positive Y horizontal and positive X up, then really we're looking for Y. But I will let you decide which coordinate system. Okay, regular. But where would you like to put the origin? So Kyle suggests let's use the standard positive Y up, positive X right. All right, he decides to put it such that the origin is at initial space and initial time. Okay. All right. Let's bust up our equation. And rederive our equation of motion to obtain the specific one that pertains to this particular problem. First, in the X direction, we decided to align positive X horizontally. Therefore, we know that since this is a free fall problem, the acceleration is vertical. Therefore, the X component of the acceleration is 0. Hence, all the acceleration term or all the last term of equation 2, 3, and 4 are 0, which implies that the first and the second equation end up being the same, and the third and the fourth tells us that the X component of velocity is the same as V naught X. All right. Similarly, this is a 2D problem, so we can use vector. This is V naught. Therefore, V naught X is here, and V naught what is here. So V naught X, by property of vector, is going to be equal to V naught cosine of theta. Cosine of minus X is the same as cosine of X, therefore, this is still positive. Good. Those are two equations that survive in the X direction. In the Y direction, this is a free fall problem, therefore we know that the acceleration is only vertical, hence we cannot use the first equation, which only assumes that A is 0, or which can only be used if A is 0. Okay, so we've done 2, 3. Since we decided to put our positive Y vertically, then we're going to switch all our X by Y, even in the velocities. Since this is free fall, A is not 0, therefore we keep them, but we know its magnitude. It's equal to positive J, be careful Kyle, positive, 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 always positive. It's the magnitude, it's the length of your arrow, always positive. But since we have decided to use positive Y as our axis, which is up, hence we have to change the sign of the acceleration vector. So there's two things going on here. The acceleration is always positive. So as you're going to plug numbers and substitute the value of G, you're going to substitute it with positive 9.8. Excellent. Therefore, we have y is equal to y naught plus v, this is supposed to be y, sorry, v naught y t minus 1/2 gt squared. And then vy is equal to v naught y minus gt. And again, g will be positive 9.8. G is always positive 9.8. Always, always, always. Excellent. Next one. We have decided, well, Kyle has decided to put the origin at the initial time and initial space. Therefore, y naught goes away. And lastly, again by property of vector, let's substitute the functional form of v naught y. And since we draw it to make our life easy, we identify the fact that v naught y is negative. Because sine of negative x is negative sine of x. Hence, our equations become y is equal to negative v naught sine theta t minus 1/2 g t squared. And in this case, if you put the negative side up front, make sure you only use absolute value. Vy is equal to, and here it's personal. If you decide to keep theta as negative 20, then don't put the negative here. You will pick up the negative sign as you calculate it. Up to you. That's a personal choice. I like to put it directly on the equations. Don't forget to multiply both terms, v naught and sine, for the last equation. All right. This is my final equation for x, my final equation for y. So that's what I'm going to see for the WI folks at the end of your justification in words. Okay, so now the rest should be easy. How far horizontally do we need to, whoops, yep, oh, yeah, oh, thank you, squared, thank you, thank you. Thank you, Ray. So we're looking for, obviously, x. Therefore, let me number those equations. 1, 2, 3, 4, 5. So obviously, we're going to use the first equation, right? That's the only one that has x. The problem is, and I apologize, I should have put vx. So we know that this is this vx. And not this v. The problem is we need to know t, and we don't know t. So we hit a situation where there is only one equation we can use, but there is two unknown. Therefore, this implies that we need to combine another equation, or that we need to figure out the time first. So we need to figure out the time it takes to go from this point to this point. Therefore, whatever equation we're going to use to obtain the time, it needs to be applied between those 2 points, initial and final. Do we know anything about this point? Excellent. We're going to use equation 3. But then what are we going to put for y? Is it going to be negative 9 or positive 9? Where is this point located? And that's where the diagram and the current stem will save us. Is this point located below our x-axis or above our x-axis? It's located below, right? Therefore, we need to use negative. Excellent. Yeah. Therefore, equation 3 will become negative 9 is equal to negative 15 sine of 20 time minus 9.81 divided by 2 times t squared. That's obviously a quadratic. We're going to solve for this and obtain 2 solutions. One will be positive, the other one will be negative. We're going to keep the positive solution for time, always positive, and we're going to plug it into our x equation. Which, I apologize, I forgot to simplify this one. This should be 0. My bad. I should have mentioned that since I located the origin at the initial time, initial position, my initial position in the x direction, or x naught, was 0. So really, the equation is x is equal to v naught cosine theta t. So I'm going to plug this t right here, and then substitute v naught by 15, cosine theta with cosine 20, and then substitute the positive value of t into the equation to obtain a value for x, which obviously is positive, because this point is on the right side of my y-axis, therefore positive. Okay? So the trick here is this. And that's why having the simplified version and your diagram help you not to forget the negative sign. Otherwise, that's the common mistake. The other common mistake is to forget this negative sign. So either you put in your equation right there, or you keep it here. But either or. Don't do both. Otherwise, you double dip. Okay? But if you do a diagram, you see clearly that your v naught x is positive right here, and you see clearly that your v naught y is negative. So your diagram with your coordinate system will always either help you identify the signs of whatever variable you're going to use, or confirm the signs of the variable you're going to calculate. Okay? Questions? Is everything okay? On number 3? All right, Crystal. Whoever asked for it, Kyle. Hello, where are you? That was for you. All right, let's move on then. 7. Oh, 7 is optional. You sure you want to do this? It's not going to be on the test. Oh, I'm sorry, Kyle. I thought you asked for 3. So, I'm sorry, whoever asked for 3. Before you asked for 3, Kyle, at 5:10, you typed 3. Sorry, my bad. Maybe you were talking about a different 3. So I'm confused about how to solve anything without given the variables. Okay. So let's give it a shot. Again, this is optional. This is a little bit more challenging, so you don't have to worry if it's a challenging one. This is not something that I'm going to ask you on the test. Okay. Roger, Kyle. So we have a mongoose. This is actually a fascinating situation. It will always be hit if those conditions are satisfied. So as long as you aim directly at the target, there's always going to be the same relationship. Oh, okay. So a mongoose is up on the tree. So let's follow the same setup. Oh, it's been a long time I never did this problem, so let's see how that goes. Theta, this is the target. This is the height. And this is the distance. Okay. We are aiming directly at the mongoose, okay. And the mongoose, let's go at the same time as the rock leaves your hand. Okay. So those are important conditions. That means that if you have impact, the time will be obviously the same, and obviously the position will be the same. We mentioned this last week. Every time you have a collision, that must be satisfied. Should the rock always the mongoose as it falls, provided that the rock gets to the mongoose before it hits the ground? Okay. Yeah. Okay. Hint, use the fact that both the rock and mongoose share the same location. Oh, okay, so everything is there. Okay, so we need an equation that defines the trajectory of the rock and equations that describe the trajectory of the mongoose. And we know nothing about time. Therefore, we need equations that are expressing the position. How are we going to do this? We are expert in getting our equation, so I'm going to write the simplified equation for this particular problem. I go all the way over here. So the x equation for the rock will be x. Obviously, x naught is 0. Please stop me if there is any simplification that I'm mentioning that you're not sure where it comes from. And the x component will be this. And then Vx will be V naught cosine theta. Does everybody agree with my x equation for the rock based on the diagram and the choice of my coordinate system? All right. Let's look at the y. Y cosine, because I'm doing the f component, this is V naught. So if this is V naught, then the V naught cosine is here, right? And the Vy is here. So V naught is the adjacent, therefore cosine, and the y component is the opposite, therefore sine. Okay? So the y component, y naught is going to be equal to 0 again, due to the choice of the origin. And then this time, the y component of the initial velocity will be the sine. And then for the v, same thing, the y component is the sine, minus gt. Again, free fall, therefore I change the sign of my acceleration. And the last one, which I don't think I will need, but just for good luck, minus 2 gy. Okay? Is there any questions regarding to the functional form of my simplified equation for this particular system? So what I want to do is I want to write all the equations for both systems, figure out what's common, combine them, and eventually, as I finish the algebra, I'm going to end up with blah blah is equal to blah blah. Then the proof is done. So it's a proof problem. What about the mongoose? Can anybody give me the x equation? Because really, that's what's different. In the same coordinate system, does the x component of the mongoose changes with time? As you look at your diagram, the mongoose is going from this point to that point. As the mongoose drops from rest, from here to where it's going to be hit, is its x coordinate is going to change? Obviously not. Excellent. Do we know its value based on what's given to us? Look at your diagram, and do we know this distance? Don't look at my diagram, it sucks, but look at the one on the problem. Is there any dimension that are given to you? Yes, there's 2, D and H. Any one of those 2 refers to what we're talking about? Yeah, excellent. It's right there in front of us. No biggie. That's easy. So obviously, as the mongoose drops, the position remains the same, and the problem is telling us it's at a distance d. Easy. All right. What about the x component of the velocity? Is the velocity of the mongoose in the x component going to be constant as well as for the rock? Or is it going to change? The mongoose is also subjected to free fall. So if the mongoose is also subjected to free fall, if the x component of this velocity will change. Definition. Okay, so what does that mean about the x component of velocity? The x component. I'm only concerned about the x. We're doing Vx. It is a constant, right? Same as the rock. Perfect. Now that we know it's a constant, do we happen to know its exact value? As we look at our diagram and realize that the mongoose is falling vertically from this point to this point. Does he have a x component of the velocity? If he drops vertically? This is a very simple question, not mathematics. That yeah, excellent, right? If he had a velocity in the x direction, he will go towards the left or towards the right. Perfect. So Vx is 0. Okay, we're just looking at the diagram. Okay, now let's look at the y. Initially, based on this coordinate system, thus our mongoose has an initial vertical position, which means, do we need to keep y naught? Excellent. Obviously we do, right? We are above here. Do we know the exact value of y naught? Yeah, it's given to us. H. Excellent, Brian. Do you agree, Crystal? It's right there. It's given to us in the diagram. So we just need to grab it. That's where it starts. Yep, just H. If you look at the diagram, they show us that this distance is H. And this is where the mongoose starts, right? And it's a vertical direction. So y naught is H. Okay. The mongoose drops from his tree. Therefore, what is his initial velocity in the y direction? The problem tells us that the mongoose lets go. You're referring to acceleration, Crystal. I'm asking about the velocity. The keyword mongoose lets go suggests what about the velocity? Same with Crystal, pal. You're talking about acceleration. I'm asking about the velocity. What does the keyword let's go mean? Excellent. Tyson and Michael. Obviously, let's go is the same as dropped. So the Vy component is 0. But it's still subjected to free fall acceleration. Negative 1/2 gt squared. Yeah? Does that make sense? Perfect. Vy, similarly, we start at 0 minus gt. And we don't care about that one, but let's just write it for good luck. Negative 2gy. All right. So those are the equations for each system in a same coordinate system. Now, technically, this is x rock, 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 rock. This is all pertaining to the rock. Rock, rock, rock. The only one that's common is obviously G. G is common to all. And this is the mongoose. M. 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 Okay. If they collide, what does this collision implies on some of those kinetic variables? Something we talked about last week, something I just mentioned, and something that is actually given to you in the problem. What must be common between those set of equations if the rock actually collides with the mongoose? Excellent. Their x better be the same. That means this guy is the same as that guy. The time better be the same. So all those Tm better be equal to Tr. And Crystal, can you refine your statement? When you say position, do you confirm Tyson, or are you being more complete and would like to include something else? Position, as we've seen on chapter 2, refers to two things. The x, as Tyson suggested, and yeah, you're right. Something else will be different. It's written in the problem. All you have to do is read it. Third paragraph. We talked about this last week. You've taken notes. It should be your notes. You should have your notes with one page that says collision, not to forget. I said that three things were common. You got to take notes, otherwise you're not going to survive this class. What does your note says about collision? And I said it when we started this problem. Thank you. And the why. That's what the problem asks you to do. Express both x position and equate them with each other. So you're going to take equation 1 and equate it with 1 prime. Then do the same for the y position. You're going to take equation 2 and set it equal to 2 prime. And use the fact that time is also common. Therefore, as you combine those two equations, 1 and 1 prime and 2 and 2 prime, you're going to use the fact that Tm is the same as Tr, just call it T. Continue that proof, and as you finish the algebra, you're going to end up with blah 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 is equal to blah blah blah, exactly the same. That will confirm that the proof is correct, which implies that if you aim at the mongoose and you shoot your projectile at the same time as the mongoose or the target moves from rest, as long as you have enough initial velocity, you will always hit it. Always, always, always. It's a cool little problem. But again, that's why I put optional. It's a proof. Some people love them, some people hate them. Proof will come back though, whether you like it or not, in 274. Okay? So please finish it up. That's just, from there, it's just algebra. Equate 1 and 1 prime, equate 2 and 2 prime, do the algebra, and as you combine those two equations together, use the fact that the time obviously is the same, because if they meet the same position at different time, they will miss each other. Oh yeah. I love proof. That's how I used to love teaching 274. Proof every 5 minutes. But those are so cool proofs. It's awesome. I don't know if Brother Van is doing much proof. If you are going to take Math 311, that's all you're going to be doing in this class. So if that's some math class that you are interested in taking, or you have to take based on your major, this is a cool class too. Except it's on Hyperspace in algebra. And I'm sure you do proof in math, so I mean, you used to it. All right, perfect. We still have 5 minutes. Any other conceptual question you may have, or anything of that sort? All right, so let me release the board so you can re-navigate what we've done. Let's take a break. 5:57 on my clock, so let's meet again in 10 minutes. When I come back, I would like you to, I would like to go over Newton's method for chapter, I don't know where we are, 2, 3, 4. I'm guessing it's 5 and 6 in your book, so that you are ready to start. Hopefully you did watch the lecture for today, so you should be good. But then you can start working problems over the weekend, because Newton is going to be a challenging topic, and we are going to spend a good 2 weeks because it's so complex, but it's fascinating. So again, I will go over the method. You'll see it's very fast, 7 steps, and within the second step, 5 more. That's it. So make sure you take good notes, write them down, and every problem that you work out in Newton, bang, 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 put that method step by step. And then you should be good. Then it's easy. All right, and then that should only take me 20 minutes, and then we'll make groups. I will make 3 groups for the conceptual question. So if you're interested in interacting with each other and collaborating about the conceptual vector questions, then you can move yourself to the first group room. If you're interested in collaborating with respect to the kinematic 1D question, then you will go to the second room. And if you're interested in working in the kinematic 2D problem, then feel free to join the third room. Because the last 2 questions are just definition, so we don't need to talk about this. That's something you already know. Okay, quick break. Oh, sorry, I talked too much. 58, so 608. Kyle, do we have class on Monday if the exam's on Monday? Absolutely, Kyle, we do. Michael, yep, the exam is at Kapiolani Community College. There is a link on the course website, so you can check the hours and the time and the logistics and blah, blah, blah. And for 2 of you, will be at OICC. And you already know about this because I saw your email. Thank you. You don't have to take an appointment. You can just show up whenever you want. Just remember that you have to take the exam in one shot. You cannot start it, go back home, and finish it up. All right, so Newton forces. Absolutely, Cynthia. You choose between Monday or Tuesday based on your schedule. Up to you. Newton has 3 laws. The first law, or I'm going to start with the second law. The second law states very clearly that if you add, that's what the Riemann symbol means. You should have seen this in your calculus class. If you add a bunch of forces, F, which are also vectors, which means that we can use the exact same technique as the vector chapter to characterize them. If you add a bunch of forces which are external to your system of mass m, this will cause an acceleration. That's it. So now we know the source of that acceleration. Since we only know about one, which is the acceleration due to gravity, obviously now we can make the link. If A is equal to 9.81, it means that the only force on the left-hand side is the force due to gravity. And we're going to call it weight. You will also notice that this is a vector and this is a vector. Since it's a scalar, the direction of the acceleration will be exactly the same as the direction of the net force, the sum of all those forces. Perfect. If the acceleration happens to be 0, then the right-hand side is 0. Therefore, we end up with Newton's first law. That's what we call equilibrium. It means that if A is equal to 0, using the basic definition of kinematics, dv dt is equal to 0, which means that dv is equal to 0, which means that v final minus v initial is equal to 0, which means that v final is equal to v initial. That's very, very important. Equilibrium does not mean that the system does not move. All it means is that if the system had a particular velocity, any kind of velocity, 1, 2, 3, 0, the velocity will remain the same. Okay? And that makes sense because the velocity is not an invariant quantity. If you measure the speed of the car passing you by as you're at rest, you may measure 10 miles per hour. But if you yourself travel in the same direction at 10 miles an hour, if you try to measure the velocity of the car with respect to you, it will be 0. So obviously the velocity is dependent on your reference frame or your coordinate system, whether it's moving or not. Third law, So the nice thing about those two laws, first and second, is that they are all being applied to a particular system. You apply these two laws to one system. And this system is the one that has mass m. Always to one system. The third law is never applied to one system. The third law is applied when you have two systems connected to one another. Which means if you have system 1 and system 2 and both are in contact, if you decide that system 1 is your system 1 is being subjected by an external force from system 2 acting on system 1. This force in this case would be towards the right, and it will have a particular magnitude. If now you identify S2 as your system and look at the external force acting on this, system 2 will be subjected by system 1, by a force from system 1, which will be horizontally towards the left. Those two forces have the same magnitude. But the negative sign here tells you that their direction is opposite. So the third law is never applied to one system. The third law is always applied between systems when you have more than one system connected. That's a big distinction between the first and the second and the third. Perfect. So those are definitions. So the third law is like when the fly hits your windshield. Exactly. Or vice versa. And this law is true whether this is at rest or if this is moving at a constant velocity or this is moving at a particular acceleration. Doesn't matter. This third law is always true. Wonderful thing. Okay, which, if you think about it, is problematic with respect to a philosophical approach, because it pretty much suggests that nature is watching you and will create an equal force but opposite direction towards you every time you interact with it, which is a little bit troublesome at first. But this will be picked up in Physics 274 in quantum mechanics. Oh, I was saying that the third law has an effect on the philosophical approach of reality and nature. It means that pretty much if you push a ball with your finger, you apply a force onto the wall. As soon as you do this, the wall is going to know about it and is going to apply the exact same force in magnitude but opposite direction towards your finger. If you decide and you think, without telling anybody, especially the wall, that you're going to be using 1 Newton force, somehow the wall is going to know. It's going to read your mind and apply the exact same magnitude. And if you change your mind, it'll change that 1 Newton magnitude with 10. It is going to know instantly. So, fun thing to think about. So, what I would like to go over is the method in applying the first and the second law. So let's make another screen. So make sure you take good notes of this, watch the lectures. Lectures should complement. Yes, Jenny. Kyle already has this. The tests have nothing to do with our meeting. Since you can take the test anytime during the day, and you have an additional day on Tuesday, we're still going to meet on Monday and continue on Newton. So let's go over the method as we apply the first and the second law. I'm going to use another screen. First is to identify your system. This is the important step that most people decide to skip. And every time they skip it, I don't have to even look at the rest. You got 0. The rest is trash. Identify your system. This is the system that will usually have a particular mass. This is a system that will be subjected to the external forces acting on it. Depending on which system you pick, the left-hand side, which is the sum of forces, external, will be different. And we're going to see this as we practice problem. So the first step is to clarify to yourself which system are you going to apply, either the first or the second law. Second one, that's when you identify the left-hand side, which is all the external forces to your system. And the external is crucial. You're only concerned about forces coming from the outside acting on your system. You're not concerned about internal forces, only the external forces. And all those forces are contact forces, which means that they must be in contact with your system. So if you don't skip the first step, they're very easy to identify. The only exception to the rule is one force, which will be the weight. Weight is a fundamental force because they're related to gravity, and this one is able to act at a distance. That's the only exception. Every other forces will be contact forces. So all you have to do is draw your little diagram and look at every contact that your system has with its environment. Once you have done this, you want to do what we call a free body diagram, which means that you want to draw every one of those forces with their mathematical description, which are vectors. And you're going to put them in a particular diagram. This free body diagram implies three things. First, your actual forces, nicely and clearly labeled. Second, it will include a coordinate system. And this is where you're going to be able to pick the coordinate system that you like best. And you will be able to pick anything you want. Third, as we've seen in the vector chapter, the only way for you to add vectors, which is the left-hand side of Newton's first and second law, is to express them in component notation, or unit vector notation, which implies that you know the direction of your force with either your x or your y-axis. Therefore, you need to figure out all your force directions with respect to your current system. That's why the current system is going to be useful. Then you can express it in component notation easily, like in chapter 2. This is all the science right there. Those are the first three most important steps ever. Once these are done, then the rest is just math, because then you apply Newton's law. First or second, which means that you look at your free body diagram, calculate in your head or on paper the component vector, the component notation of each of your forces showing up, and you just add them up, because Newton's law is about adding those forces. That's the left-hand side. That's it. And then you're going to solve for your system of equation. That's the algebra part. Okay? Newton's law is a vector equation. So as you write the force is equal to ma or 0, if you have a one-dimensional system, you have one scalar equation, as you've seen in the vector chapter. If you're working in a two-dimensional problem, you're going to pick up two equations, one along the x, the other one along the y. If you're working with a 3D problem, then you're going to pick up three equations. That's simple. 4D, physics 274, four equations. So you're going to pick up as number of scalar equations as the number of dimensions. So here, this is solving a system of linear equation of n by n. 1, 2, 3, or more. If you end up having to consider more than one system, and you have a set of equations for each system, and if you have to combine several equations, 2, 3, 4, you multiply the number of equations by the number of systems. So in this class, you're going to have to solve a system up to 4 by 4 easily, sometimes 5 by 5. That's where high school algebra is going to be crucial. So make sure that you review your high school algebra about how to solve a system of linear equation. Revisit your substitution method, your addition method, your Gaussian method, your linear algebra method with a determinant, whatever works for you. But you have to be able to do basic algebra. Otherwise, you won't be able to pass this class, which relies specifically on algebra and calculus, as we're going to see with dot product and cross product. Okay? So this is an opportunity for you to revisit all that stuff. That's it. Those are the 5-step method for Newton. Now, what I want to do now is I want to investigate the second step. what are those stupid external forces that we're going to be considering in this class? Let me use another board. As you go through the list of identifying forces, since I've been saying that the third step is the most important step ever, the free body diagram. If this is wrong, the rest is wrong, and I have to look at it. If this is right, statistically, the rest of the problem will be right. Then you need to make sure that the identification of those forces is correct. So let's go through the list of all possible forces that we're going to see in this class in step 2. First, excellent. Now, I'm not going to use the word gravity just yet. I'm going to use the word weight. And we're going to revisit weight in chapter 13 and make the correlation between gravity. We could use gravity, but gravity is nasty in its functional form. And since we're going to do all our problem as the surface of the Earth, then the functional form of the general gravitational force can be reduced to a very simple and much nicer functional form, which we call the weight. So we'll work with that. So the weight is the first one. The weight is always the easiest, and that's the first one you should always think about if your system has mass. First, we know its magnitude. It's defined as mg, the mass of the system that you have identified in step 1, times the acceleration due to gravity, that 9.81. That's what I was stressing out, that g is always positive 9.81. You cannot put a negative sign in there. This represents the magnitude of the force weight. Got to be positive. And you also will also know its direction, which follows the acceleration due to gravity that we've seen earlier. It's always going to be down. So that's the easiest way ever. Start with that one. Second one is the normal force. For you to ask yourself if there is a normal force or not, look for contact. Is your system in contact with a surface or another system? And you're going to have a normal force associated with each. That could be 1, that could be 2, that could be 3, 4, 5, 6, 10. The nice thing about the normal force is we always know its direction. The direction of the normal force is always perpendicular to the surface, which means that it can be 50-50. It can be away from the surface or into the surface. For you to figure it out, use the second part of the definition. The direction of the normal force is not only perpendicular to the surface that makes contact with your system, but since it's an external force and acts on our system, as I mentioned in the definition, then you only care about the one that is directed towards your system. So it's not only perpendicular, but it is also acting on your system. This will give you the correct direction. Perfect. Thing to be careful and take a note. You never know the magnitude of the normal force. So don't ever, ever squeeze the magnitude of the normal force, say, as mg. Ever. Please don't. You're always going to hit dirt if you do this. So never assume its magnitude of the normal force. You will pick up its magnitude as you solve for the equation naturally. Second, any pushing or pulling, such as a spring, a rope, a finger, whatever. Usually those are given to you in the problem. And remember, all those forces are external to your system, act on your system, and are contact forces. So they're usually very identifiable. Whoever is pushing, whoever is pulling. In this class, you should be having any ambiguity about whether it's pushing or pulling. Common sense will always allow you to do so. In CH70, things are going to change, but we will see a fix to this. And the last one is friction. How do you know whether there is friction? Well, first of all, we're only going to consider two types of friction: surface friction and drag force. Surface friction is going to be the most common one. We're only going to see drag force for one particular case. So we're only going to be dealing with surface friction, which means if your system is in contact with another system or a surface, and there is friction between the two, whether your system is moving or not. So for you to be able to decide whether you have to include friction, look for the keywords US and UK. Those are the coefficient of static friction and the coefficient of kinetic friction. If there is any friction in the problem, I will give you those two quantities, or I will mention them in the problem. So as soon as you see those, you know right away, okay, I need to consider friction. If you do not see any of those two, US and UK, you don't have to consider friction. Therefore, you only have 3 types. And that's it. So if you follow that order, you will neither forget forces nor invent forces, which is what a lot of people tend to do. You're always going to stick to the list, and you're always going to get it right. Very, very easy. So please, put those 2 methods or 3 screens, definition of Newton, Newton's method, and the list of forces on the page next to you, written in your own words, and work out every problem with this method next to you. And life will be life and easy, beautiful and easy. And it will smell good too. If you don't, you're on your own. Okay? Questions on Newton. Hopefully this should echo the lectures that you've already watched for today. Is there any discrepancy between the lectures that you watched and what we went about? All right. Yoo-hoo! That means I did a good job, hopefully. Oh. Good question, Jenny. No, they both surface friction. US is for a situation where there is no relative motion between your system and the surface. And UK will be used when there is a relative motion between your system and the surface. Drag is going to be called FD. And the big difference between FD, the drag force, and the surface friction is that the kinetic friction is always going to be constant. So that's nice. The static friction is going to be variable. But it will always depend on the normal force. So if you figure out the normal force, you can deduce the static friction. So they're like married to each other. The drag force is the one that will not depend on the same property as the static friction or kinetic friction. This one will depend on your velocity. So the faster you're going to go, the bigger drag you're going to feel, like on an airplane. And it will depend on the medium. So if you fly through air, that will most likely depend on V squared, I believe. But if you go through a higher density medium, such as oil, then the drag force can be considered as a function of the velocity only. I'm sorry, don't put me on this, it may be the opposite. But we'll go back to that. Okay? 2 hours. Good question, Crystal. Your first test will be 2 hours long. First test is always the easiest one. Next test, second and third, will be 3 hours long because we have way more to cover. What do you think, Michael? What was the time limit that I was suggesting you to meet as you work out problems over problems over problems? I keep saying that you need to do it in how many minutes? Whoa! No, not 5 minutes. Yeah, thank you. 15, right? So if you have a 2-hour test, you should expect 8 questions. But you know, some questions you can do it in 5, Henry. And you should. So yes, roughly 8 problems. I believe the WI has 8 and the non-WI has 7. So that means you have an extra 15 minutes for the non-WI. While WI you don't care because you have no time limit. Okay, so you should have time to review and check. Please be careful. Let me take a good note of this since we're on the test topic. If you have a question, let's say question 3, that has several parts. Make sure that you indicate in your solution which part you're doing. So write them down. If I don't see which part you're doing, I won't even bother looking for it. Am I making myself clear? It doesn't take that long to write down which part you're working on, so make sure you do it. Okay? Especially for the WI, because your list is going to go all the way down to F, G, H. So if you want points allocated for each part, make sure you write it clearly. This is part 1. This is part 2. So usually this comes after using the method and simplifying all the equation. Then you can tell me, okay, now I'm going to solve part A or part B, whatever. Make sure you show it to me. I will not bother looking. I'm just going to do a quick glance. If I don't see the correct answer, 0. Okay, but if I see, he or she's working on part A, and there is some steps that are being shown, okay, let me try to figure out the reasoning. And if the reasoning is correct, you'll get partial credits. Okay? And usually, if your reasoning is perfect, but you just happen to make a small mistake on the calculation side, as you use calculator, you will lose only a very, very minimum amount of points. So be concerned about the process, not the final answer. Lastly, do not forget, as you have extra time and go back and check every problem that you do, or as you complete a problem, do not forget your units. I will take points if units are not present. But I didn't mean that you need to include units on every calculation that you do. No, no, no. Only on your final answer. Okay? So only on your final answer. Do not forget the units. So always remember to do a last sweep and check every final answer. What I would suggest is circle them so it's clear, nice and easy, and bang, include the units. Only for the final answer. I will take points if I don't see units. Excellent. The only exception is if you have an obvious vector problem. Then screw the units. That's just a math problem. Yes, Jamie. Full sentences, or if you don't want to use full sentences, it needs to be readable for me to understand what you're doing. So if you want to use arrows or whatever, pictures, as long as I understand it, it's fine. That's the reason why I was stressing everybody to show me an example of your workout problems so I can tell you this is good, this is good, this is good. Then just duplicate what you showed me. If you never bother showing me anything, you're on your own. See ya. I don't want to be ya. No, no cheat sheet. You're not allowed to bring anything except, good question, thank you, an ID so they can identify you. Make sure it looks valid. Pen, pencil, whatever. Whatever you use. An eraser, whatever you use. A calculator. And something to keep track of time for the non-WI. Because as you've seen the syllabus, there is penalty. If you're WI, you don't need this. That's it. I will provide everything else. You need to know all your formulas. Michael, my last project for if we drew a problem out nicely. Well, here so as well. If you draw your diagram and you show me the current system, and then you show me the equation to use, if they're consistent with the current system, I will give you partial credits because then I will have the feeling that you follow the method. That's what I'm after. If you follow the method, you will get partial credits. If you decide to ignore the method, I will have no mercy. I'm just going to look at the answer. If the answer is correct, you got 3 points. You know what you're doing, you don't need me. But if the answer is not correct, you got 0 points. Nibble for non-Wi-Fi. Non-WI. If we show our work and the answer is a little off, of course. If you show your work and you follow the method that we done in class and everything is perfect, but the numerical answer is a little bit off, don't worry. You lose like half a point, a quarter of a point, nothing, almost nothing. So you will get plenty partial credits, absolutely. All right, Brian, cheat sheet, no cheat sheet. I will give you extra pages. Write it all out until the answer usually. Perfect. And in Python, with the only formula we need the kinematic ones. For this particular test, yep, you will need to know, well, all the formula for vectors. You know, Pythagorean theorem, sine, cosine, arctangent, blah, blah, blah. And then for kinematics, what do you need? You need to know the definition of basic kinematic concepts, acceleration and velocity. And then to work on problems, all you need to know is those 4 equations, right? That's it. You can redrive everything else. Perfect. All right. So, let me send the quiz to everybody. Oh, let me send it to the list. Easier. Quiz 2. Share. Where are you? Wait. Where's my share option? Ah, here we go. So I'm going to send it to the list. The right list. Up. Are you sure you would like to open this form to user from us, University of Hawaii? Yeah. Okay, sent. So you should all have it on your email right now. And then I'm going to create 3 groups. As you will look at the quiz, and you will see that question 1, 2, 3, 4, 5, 6 are all about vectors. Oh, where's my pen? Okay, so Q1 to 6 is about vector. Q7 is 1D, and Q8, oh wait, 7 and 8, and then 9 is 2D. And the other one is their definition. So I'm going to make 3 rooms. Room 1, room 2, room 3. So look at the quiz. You should have received, wait, double check. You should have received the email by now. So access the quiz, look at those questions, and identify the ones that you feel the least confident. If that's vector, please join room 1. If you don't feel as confident about kinematic 1D, please join room 2. And if you like to exchange ideas and methods and blah blah about the 2D, then join room 3. You should be able to go from room to room. Okay? Go for it. Let me create those stupid rooms. So I'm not going to move you. You're free to move wherever you want. You should be able to drag yourself. Hey, how come you only created 1 room? Oh. Okay. Room 1, room 2, room 3. So this one is about the vector. So from Q1 to Q6. Room 2 is 1D. And that's Q7 and Q8. And then the last room, 2D, that's Q9. Oh, 7 and 9. Wait, there is no 7 and 9. Henry. There's at least one person per room, so I'm hoping that it got fixed. Please let me know. Anyway, you should be able. Whoa. Ah. Oh, you mean on the quiz? Oh, thank you. Oh, what the heck is this? Oh, brother. Thank you. There. Thank you, Henry. That should be fixed. Thank you. So if you do a refresh, reload, don't worry, Jamie. Just do a refresh, reload on the quiz. Let me check everything else. Multiple choice, question 5, okay. 6, 7, okay. 8, alright, okay. Thank you, Henry. Thank you. Okay, go for it. Oh wow, nobody in Kinematics 2D. Oh, interesting. Alan is the only one in Kinematics 2D. Ian, Jamie, Kyle, Yanan. Nobody wants to join him? Otherwise, maybe a little bit alone. Only if that's what you're interested in. Oh, okay. Then don't worry. Do your thing.